So gender roles can be
No, it's not because the data that I witness na salita was everything about anything about Bumizo are Eba Mamalon.
Sorry.
Of we didn't know why I was able to hand the Imbo, but I will come down.
Come on, my hand there.
But how somebody going into the workforce, there's often this pressure or this power dynamic between men and women who and sometimes between genders to take advantage of others in the workplace and school. So yeah, we discussed that dynamic between like the power hierarchy between genders. That is really harmful and really difficult to talk.
The rest of the slide. In terms of gender inequality and gender-based violence, the economic issue with that is that a lot of things going on with the workforce, especially male-dominated, so if women start entering these types of workforces, there's more of a male presence in them. And that can cause women to feel pressured into doing certain things for their bosses, which in any workforce, we all know that is very unethical, and it does cause people, women and men, because it goes with women causing this, to want to leave these workforces. And some impacts from this is that a lot with gender-based violence is mainly focused, or at least a lot of information focuses more on the women's side and not just the male side. And with these types of violence, it can cause victims to play roles, it can cause women and men to play these roles where they're in like such small power stage where they're not able to get or ask for help, because especially for the men, there's such a broad amount of norms towards men that they're powerhouses, they're able to get this, and also not experience the types of violence they are. It does require
The University of KwaZulu-Natal's College of Agriculture, Engineering and Science is committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally as a center of excellence. Agriculture, Engineering and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture, engineering and science activities in the region. The college comprises 5 schools: agricultural, earth and environmental sciences, engineering, chemistry and physics, life sciences and mathematics, statistics and computer science. Engineering is offered on the Howard College campus, agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westville campuses. Exceptions are agricultural engineering, which is offered in Pietermaritzburg, and geology, which is offered at Westville only. To compete with the best and to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering, and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. For example, we are the only university in South Africa to offer a fully accredited agricultural engineering degree, and one of only 2 universities in the country to offer a BSc in land surveying. Our postgraduate food security training program is the only one in the world, and we have the widest range of agricultural disciplines at any single South African or African campus. The choices of degree and the options on offer may seem confusing at first. Engineering degrees are more specific, and the options are usually career-focused. Emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers 7 different professional specializations. There are also degrees in land surveying or geomatics and property development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general degrees with a lot of flexibility. In this case, students have the choice of studying a BSc M stream in maths, physics, computer science, and statistics. All of these have a strong mathematical component. The other option is a BSc LES stream with a focus on the life and environmental sciences, with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the end of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Upalinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCON-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering, and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering, and Science prides itself on its graduates, who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering, and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. College has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating hunger in Africa. It offers food security training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice is the Center for Research in Environmental, Coastal, and Hydrological Engineering, or CRESH. It deals with the interaction between engineering and the natural environment. The Mechatronics and Robotics Research Group in the School of Engineering provides an excellent research and education environment for its senior undergraduate and postgraduate students. Judged one of the best research centers at the university, the Center for Plant Growth and Development focuses on high-quality research in the plant-based disciplines of plant physiology, plant molecular biology, and ethnobotany. The Center for Quantum Technology deals with physical phenomena at the microscopic level. Quantum physics led to the development of the transistor and the laser, and is currently being used to develop quantum computers and quantum cryptography. The college is committed to access and readdressing the disadvantages and inequities of the past. The highly successful Unite Engineering program and the Science Access Foundation and augmented programs offer alternative access to university, equipping students from disadvantaged backgrounds with the skills and knowledge to pursue their degrees of choice. Both these programs contribute significantly to advancing Black African scientists and engineers in South Africa. Staff and students contribute to a number of outreach and community initiatives that focus on social responsibility, sustainable development, and upliftment of the wider community. The college also engages in activities involving the pursuit and understanding of science, engineering, and technology through exhibitions, festivals, and roadshows that target high school learners and the general public. The college has minimum entry requirements for its programs. These differ from degree to degree, but all require a national senior certificate and minimum performance levels in mathematics and either physical or life or agricultural sciences. For those who do not meet the minimum requirements, access programs are available. Additional information and brochures can be obtained from the contact information accompanying this video. The College of Agriculture, Engineering and Science is proud of its contribution to the university, the region and the country.
UKZN is one of the best. I definitely understand it's one of the best in South Africa. So for me, there was no other institute that I would have preferred other than UKZN.
With the best facilities here in terms of laboratories, in terms of equipment, in terms of human resources, in terms of literature.
UKZN is one of the best universities in the country that teach agriculture or natural sciences.
What I think is good about this college is the level of international collaboration that we have. We have friendships with universities all over the world, which that we're keeping up to a great international standard.
UKZN has got much more facilities and it's recommended worldwide to do your science studies here. Life begins here.
We continually strive to be academically excellent, innovative in research, and critically engaged with society. We invite you to join us or work with us to be part of this exciting team.
Okay, good evening, everyone, and welcome to today's session. We're going to be doing vertical projectile motion. So can you see my screen, which has the question, and can you hear me clearly?
Yes.
Okay. Okay, so let's begin. So this is the first question that I want to do. Question 1. A ball A is thrown vertically upward from a height h with a speed of 15 meters per second. At the same instant, a second identical ball B is dropped from the same height as ball A, as shown in the diagram below. Both balls undergo free fall and eventually hit the ground. Okay. I want to read all the questions first, and then we will start with them one at a time. Okay, so the first question is, explain the term free fall. Then it says, calculate the time it takes for ball A to return to its starting point. Calculate the distance between ball A and ball B when ball A is at its maximum height. Sketch a velocity time graph for the motion of ball A from the time it is projected until it hits the ground, and clearly show the following on your graph: the initial velocity, the time it takes to reach its maximum height, and the time it takes to return to its starting point. Okay, so we have an idea of all the questions that they're gonna ask us. So here's the drawing. We can see height h, you can see ball A. Let me just, I don't want to mess up the drawing. So there's ball A here and B. And now the first one is, let's answer the questions. 1.1. Okay. And it says, explain the term free fall. Okay, so you know that free fall is motion under the influence of the gravitational force only. Okay, so, oops. It's under the influence of the gravitational force only. So that's the only force that's acting on the objects. Okay, that's the theory question. Question 1.2. Calculate the time it takes for ball A to return to its starting point. Okay, so if we're looking at the drawing here, then ball A, from where it is, it starts at a point, oh, sorry, here's the pen. It goes up, reaches the maximum point, and then it falls back down. When it comes back to the point where it started from, it will have the same magnitude of the velocity. So if it went up at 15 meters per second, when it falls back down and comes back to that same position, the velocity will be 15 meters per second, but this time it will be pointing downwards. Initially, it was 15 meters per second upwards. On its way down, it's 15 meters per second downwards. Okay, so calculate the time it takes for ball A to return to its starting point. So let's just do it like this first. So the initial V, okay, so sorry, the first thing I need to do is choose which direction I'm taking as positive. So I'm going to say, take upwards as positive. Okay, so I'm taking upwards as positive because the ball was thrown upwards. So my initial velocity was 15 meters per second upwards, so it's plus 15. And when it comes back to the same starting position, the velocity there, which will be the final velocity, is minus 15 meters per second. Okay, so now I can calculate the time that it takes for this. So the equation I will use is VF is equal to V initial plus A delta T. Okay, so my final velocity is minus 15 because that's downwards. My initial is 15 plus. Now my acceleration, I'm taking upwards to be positive. So acceleration is going to be minus 9.8 delta T, which is what I'm trying to find. Okay, so at this stage, you should be able to put this into your calculator and get an answer. I'll just write out the extra step here. So minus 15 divided by minus 9.8 is equal to delta T. Okay, so the answer you should get is delta T is equal to 3.06 seconds. So that is the time that it takes to return to its starting point. Okay. Okay, so let's go back up and see. Okay, so 1.3 is calculate the distance. Sorry. There's another thing I wanted to show you here. This is one way of calculating the time. The other thing you could have done, so let me just show you this. Or we could have said that V initial is equal to 15 meters per second. And we could say that V final is equal to 0 meters per second. So now I'm taking the part from where it started to its maximum height. Okay, so 0 meters per second is at the maximum height. So if I do that, I can use the same equation, as above, to find the time it takes to reach the maximum height. Okay, so VF is equal to VI plus A delta T. VF is 0. VI is plus 15. Acceleration is minus 9.8 delta T. And if you solve this, you will get delta T is equal to 1.53 seconds. Okay, and that is the time to reach the maximum height. Okay, time to reach the maximum height. So if the time to reach the maximum height is 1.53 seconds, what is the time to come back to that same starting position? Okay, it will just be, so delta T to return to starting position. So to return to start is 1.53 times 2, which is equal to 3.06 seconds. Okay, so they told us that the ball, let me just show you again here. It's thrown up at 15 meters per second. And how long, calculate the time it takes for the ball to return to its starting point. Okay, so what we did here was we said, okay, let's find the time it takes to reach the maximum height. And when we did the calculation, we get 1.53. That's the time to reach the maximum height. So it went up there, and then to come back down is going to be another 1.53. Okay, so that's how we get 3.06 seconds. Okay, so that's question 1.2. Question 1.3 says, calculate the distance between ball A and ball B when ball A is at its maximum height. Okay, so when you threw ball A up and it went to the maximum height, as ball A was traveling up, ball B was traveling down. When A gets to the maximum height, then what is the distance between ball A and ball B? Okay, for us to do that, we need to know when A gets to the maximum height, what is the position of A? And in that time, what is the position of B? And then we can find the distance between them. Okay, so let's do that. So for 1.3, let's start with ball A. Okay, so for ball A, at the maximum height, right? Because that's what we're talking about. For ball A at the maximum height, using the equation, VF squared is equal to VI squared plus 2A delta Y, because now we are interested in the delta Y because we want to know the distance. But I'll call it delta YA because I'm talking about ball A. Okay, so at the maximum height, what is VF for ball A? It's just 0. VI is 15, so 15 squared plus 2. And again, I'm taking upwards as positive, so A is minus 9.8 delta YA. Okay, so I can just solve now for delta YA. Okay, and you can do it as well. Delta YA is equal to, so just take it over, so it's minus 15 squared divided by 2 times minus 9.8. And you should get 11.48 meters. Okay, so that is for ball A. Now we need to find what is delta YB So what is the position of ball B when A is at the maximum height? So how are we going to do that? How are we going to know where ball B is when A gets to the maximum height? Okay, so here we calculated the delta T for ball A to reach the maximum height, and it was 1.53 seconds. So we know that the time is 1.53 seconds for the ball A to reach the maximum height. So we can calculate the position now for ball B when delta T is equal to 1.53 seconds. So that's what we're going to do now. Okay, so for ball B, when A is at max height. Okay, then delta Y B is equal to VI delta T plus a half A delta T squared. And they said here, let's go back to the question so you can see it. It said, at the same instant, a second identical ball B is dropped from the same height. So ball B is dropped. So what is VI? It's just 0. Okay. Plus a half. Again, A is minus 9.8. And delta T is 1.53 squared. Okay, and if we put all of that in here, you'll get negative 11.47 meters. Okay, which makes sense to us because we're taking upwards to be positive, and this ball was falling down, so delta Y is minus 11. So that just means that it went 11.47 meters downwards. Okay. So how do I find the distance? The distance between A and B. The distance is just going to be equal to delta YA plus delta YB. So I'm just going to add them up. So this is 11.48 for delta YA and 11.47. So we're not worried about the negative sign. That's just telling us that it's down. Okay, so 11.48 plus 11.47. And then you get 22.95. 22.95 meters. That is the distance between ball A and ball B when ball A is at the maximum height. This is the distance between them. Okay. That's the answer to that question. Okay, so let's go up and look the next part. Okay, question 1.4. Okay, sketch the velocity time graph for the motion of ball A from the time it is projected until it hits the ground. So clearly show the initial velocity, the time it takes to reach the maximum height, and the time it takes to return to its starting point. Okay, so we want to draw a velocity time graph for ball A. Okay, so while we're here, what do we know about ball A? We know that the initial velocity is 15 meters per second. So let's go through here what we've calculated. And then the time to come back or to fall the same distance again is 3.06 seconds. The time to reach the maximum height is 1.53 seconds. Okay, so we can draw the graph. So that is 1.4. So question 1.4, let's put it up here. They said draw a velocity time graph. So on the y-axis is going to be velocity. So you will write out there velocity and you will put the unit, which is meters per second. Okay. And then we will draw okay, let's do it there. That's the axis for time. So you write, oh, sorry. Okay. So we will write time, t, and it is in seconds. Okay, so you have to do that. There's marks for that. And then this point here, but maybe I can erase this bit. This is 0. Okay, 0 for velocity and 0 for time. Okay, so we know that so I'm taking upwards to be positive. Okay, so I've taken upwards to be positive. So I'm gonna put the value here at 15 meters per second. So that's 1, 2, 3 and a bit. 1, 2, 3 and a bit. So 1, 2, 3 and a bit. So here would be minus 15. Okay. And then I know that it was thrown upwards. So initially it's traveling in the positive, velocity is positive until it reaches the maximum height at some time t equal to 1.53. And then double that time, it comes down to minus 15. Okay. So there's the point there. So that's what I can draw on the graph. I know that the initial velocity is plus 15. I know this time, so this is 3.06. And I know that this one is 1.53. Okay, and so now I have to draw a straight line from my 15. From here, you'd use your ruler through there and through that point. And then the ball's still falling, remember, till it gets to the ground. So this line here must go past this point where the time is 3.06 seconds and velocity is minus 15. Okay, so this is the graph. That's the answer to the question. It asked, clearly show the following on your graph, the initial velocity. So that's there, we did that. The time it takes to reach the maximum height, at the maximum height be 0, so we've shown that. And the time it takes to return to its starting point. And so that's the time here, this, because it comes back down there. Okay, so we've answered the question. Are you happy with that? Do you have any questions? Okay, if there are no questions, just tell me so that I can move on to the next question.
It doesn't look like there are any questions. I see a couple of thumbs ups in the chat.
Okay, perfect. So I can move on to the next one. Thank you. Okay, so let's look at this example. Okay, so an object is released from rest from a point X above the ground as shown in the diagram. It travels the last 30 meters, so from B to C, in 1.5 seconds before hitting the ground. Ignore the effects of air friction. Okay, so let's just read through all the questions again. 2.1 says, name the type of motion described above. Calculate the magnitude of the velocity of the object at point B. Calculate the height of point X above the ground. And then it says, after hitting the ground, the object bounces once and then comes to rest on the ground. Sketch an acceleration time graph for the entire motion of the object. Okay, so let's do this. Okay, to get started, name the type of motion described above, ignoring air friction. This is just, so it's 2.1, free fall. Okay, so that type of motion is free fall. Okay, calculate the magnitude of the velocity of the object at point B. Okay, so in this example, the object is released from rest from point X. So it's falling down it's falling downwards. So I'm going to choose downwards to be positive. Okay. Now, they told us that from B to C, it's 30 meters and it did it in 1.5 seconds. So what we can do is, let's do this. So for 2.2, I'm going to take downwards as positive. That's the first thing. Okay, downwards is positive. Then from B to C, what is delta Y? I'll show it to you here again. Delta Y is 30 meters, right? And it's also going to be plus 30 meters because I'm taking downwards as positive, and delta T is 1.5 seconds. So I'm just writing that here so that we know 30 meters and delta T is 1.5 seconds. Okay, so let's find the initial V. So what is the velocity at B? Okay, because that's what they want us to find. So we can use the equation here. Delta Y is equal to VI delta T plus a half A delta T squared. Okay, so delta Y is 30. Oops. VI is what I'm trying to find. Delta T is 1.5 seconds plus a half. What is A? Now I'm taking downwards to be positive. So A is just plus 9.8. And delta T is 1.5 squared. Okay, so you use your calculators now and do the calculation. Tell me what you get for VI. So VI is just going to be 30 minus a half, 9.8, 1.5 squared divided by 1.5. Okay, and if you do that, you should get 12.65 meters per second. Okay, so that is the magnitude of the velocity of the object at point B. So we calculate the VI from B to C. So that is V at point B. Okay. So if you're happy with that. The next question says, calculate the height of point X above the ground. And you can see that it's for 5 marks. Okay, calculate the height of point X above the ground. So how are we going to do that? So what we can do is, let's first, we know what the height from B to C is, but we want to know from the ground to X. So we need to find the distance from X to B. Okay, that's what we need to do. So that's 2.3. Let's do that. So 2.3, let's find the distance from X to B. Okay, sorry about this writing. Okay. Okay, so how are we going to do that? Now from X to B, let's just go back here to make sure we all write this. It says an object is released from rest from point X, okay, above the ground as shown. So released from rest, so initial velocity from X to B, that's 0. And what is the velocity at B? Now in 2.2, we just calculated that. Okay, so this 12.65 is the velocity at B. So we are ready now using the equation. VF squared is equal to VI squared plus 2A delta Y. Okay, so we're trying to find delta Y. We're trying to find the distance from X to B. So what is VF squared? Well, that's the velocity at B, which is 12.65. Is equal to the initial velocity dropped from rest, so that's 0, plus 2. Acceleration is plus 9.8, and delta Y, which I'm trying to find. So see, you can just find the delta Y. And you do that now. Delta Y is just 12.65 squared divided by 2 times 9.8. Okay, and you should get 8.16 meters. Okay, so this 8.16 is from X to B. Okay, so the question is, calculate the height of X above the ground. So X to B is 8.16 and B to C is 30, so we can calculate that. Okay, so height of X above the ground, that's just equal to XB plus BC. And XB we calculated as 8.16, and B to C they told us is 30 meters. And so the answer is just 38.16 meters. Okay, that is the height of X from the ground. Okay, hope you're happy with that. Let's go see what they say here now. Okay, after hitting the ground, the object bounces once and then comes to rest on the ground. Sketch an acceleration time graph for the entire motion of the object. So the object's falling from X to the ground, it bounces one time, and then it comes to rest on the ground. Okay, acceleration versus time graph. Okay, so for 2.4, okay, we're gonna draw an acceleration time graph, and we are drawing the graph for us we chose downwards as positive, right? Which means our acceleration has been positive here, plus 9.8. So on the y-axis is acceleration. I know that it's all positive, so I can draw the x-axis here. So here's time in seconds, and then it's going on there. So I must write your acceleration and the units, meters per second squared. Okay, so you always have to label that, and then this is the 0. Now I know that the acceleration is constant because it's free fall. So I can just choose the value here, and this value is 9.8. Okay, so at 9.8, so the acceleration is all, oh, sorry. The value doesn't change, right? That's supposed to be a straight line. My line's very bad. Now there's just one part here where the object bounces. Can we not make it too long? So at this point, the object bounces. So at that point, oops. So if you're drawing the graph, we would just draw it like this and just little dots here because it bounces there and then it goes up. So that must be just a small gap there where this bounces up there. And then this is when it bounces and then it falls to 0. Okay, so the acceleration is constant at 9.8 meters per second squared until the point where it falls to 0. But we do not know when that falls to 0. So for the acceleration time graph, this is how you would draw it. Okay. Are you happy with that? Do you have any questions? That was the last one.
There are currently no questions in the chat. If they don't unmute, they can pop questions in the chat, but I think everyone is still fine.
Okay, good, thank you. So let's do one more example or the next example. Okay. Question 3. A hot air balloon is rising vertically at a constant velocity. When the hot air balloon reaches point A, a few meters above the ground, a man in the hot air balloon drops a ball which hits the ground and bounces. Ignore the effects of friction. The velocity time graph below represents the motion of the ball from the instant it is dropped until after it bounces for the first time. The time interval between bounces is ignored. Okay, the upward direction is taken as positive. Use information from the graph to answer the questions that follow. Okay, so we must understand this. So you've got this hot air balloon. It's rising vertically at a constant velocity. When it reaches point A, which is a few meters above the ground, a man in the balloon drops a ball which falls to the ground and it bounces. And here is the velocity time graph, and they are taking upwards as positive. Okay, those are the things that we have to know first before we move on. So 3.1, write down the magnitude of the velocity of the hot air balloon. Oh, okay. The graph is the velocity time graph for the motion of the ball from the instant it is dropped. So if we're looking at the graph, let's do this. So here, okay, that's, sorry, 5.88 meters per second. That's the initial velocity of the ball, but the ball was in the hot air balloon. So that 5.88 is also the velocity of the balloon. So for 3.1, it says write down the magnitude of the velocity of the hot air balloon, and it's just for 1 mark. We just read it from the graph. The initial velocity of the ball is the initial velocity of the balloon. Okay, so let's just write it down here. This is 3.1. So 3.1, it's just 5.88 meters per second. Okay. Okay, we can see question 2. Calculate the height above the ground from which the ball was dropped. Okay, calculate the height above the ground from which the ball was dropped. Okay, so now the information that we need is on the graph. Okay, so let's look at the graph and we can see. Let's talk about the graph. Okay, so what we can see on the graph is we can see the initial velocity 5.88. We can see this point here, 0.6. I'm going to need this. I don't want to mess it up too much. 0.6, where the velocity is 0. So that is where the ball reached the maximum height, because initially it was moving up, reached the maximum height before it starts falling downwards. Okay, and then we can see here at minus 19.60, and the time is 2.6 seconds. Okay, so from the graph, we can see that the final velocity is minus 19.6. We can see that the initial velocity is, and then we're going to calculate delta y. Okay, so calculate the height above the ground. So for 3.2, so 3.2, let's just write it out because we got this from the graph. VI is 5.88 meters per second. VF is minus 19.6 meters per second. Okay, and we are trying to find delta y. So we will use the equation VF squared is equal to VI squared plus 2A delta y. Okay, so substitute the values that we have in here and solve for y. So VF is minus 19.6 squared equal to 5.88 squared plus 2. Now, the value for A, remember they said we are taking upwards as positive. So A has to be minus 9.8 delta y. Okay, so this is straightforward. Then for delta y, you get negative 17.84 meters. Okay, which makes sense to us. So what is the height above the ground? So height above the ground is just 17.84 meters. Okay. So that's one way that we could do it, by using those values and using this equation. Now, the other way we could do this, another method to find, the question was, calculate the height above the ground from which the ball was dropped. Okay, so we could also find, or we could find the area under the V versus T graph. Okay, sorry, this must be a small v because it's the velocity, right? V versus T graph for 2.6 seconds. Okay, so we're going to find the area under the V versus T graph. So let's go up and see this. Okay, so if you have a velocity versus time graph, then the area under that will give you the displacement. remember? So instead of doing those calculations, instead of using the equation, which we just did, we can find the area under this V versus T graph from 0 to 2.6 seconds. So let's just look at this. So if we look at the graph, you have this triangle here from 0 to 0.6 seconds. So we can find the area there. It's the area of a triangle, so it's half base times height. The base is just 0.6 and the height is 5.88. So we can calculate the area under there. Okay, and then we can also, and then the next bit here is the graph here, it comes down here. So I'm just going to use a different color so we can see the area under here. Okay, so there's the V versus T. So the base is here. So 2.6 minus 0.6. Okay, that is the base, so half of the base. And what is the height here? It's just there. So we've got two triangles. If we calculate the area under there, it's going to give us the displacement, which is the delta y. So let's just do it like that as well. Okay. So area under that, so it will just be delta y is equal to a half base times height plus a half base times height. Okay, because there are two triangles. So for the first one, it was a half, and it was just 0.6 seconds, and the height was the initial velocity. And then the second one is a half. Now the base is 2.6 minus 0.6. And the height is minus 19.6. Okay. And then if you put that into your calculator, you should again get negative 17.84 meters. So therefore the height is 17.84. Okay, so you could use whichever method you prefer. You don't have to use more than one method. You'll only choose one. Okay, whichever you prefer. If you have time, you can use the different method to check your answer. Okay, so that's 3.2. Calculating the height, we got 17.84 meters. Okay, calculate the. So now they say, calculate the time at the point P indicated on the graph. Okay, calculate the time at point P. So, oh, sorry. So if you look here at point P is showing us, so when the ball bounces the first time, so this is the first bounce, right? So it's from this point here, which is 2.6, to this point here, which is 3.2. Okay, the ball has that velocity of 2.94, then to 0, then minus 2.94. Now, if you look at the way the graph is and what they're showing us, this is from the bounce. So it bounces up and then it's from 2.94, then maximum at V equal to 0. So at point P is when the ball reaches its maximum height after the first bounce. Okay, can you see that? And then It falls. So we can just find this point P by looking at this graph, and you see, oh, it's just 3.2 seconds minus 2.6 seconds and divided by 2, because it's just the middle of that line there. Can you see that? So that's the easiest way to do it. And then if you do that, then you would find the small time here now. Let me erase this so that I can use this red line to show you. That will give us this time interval here from 2.6 to there, this small distance. Can you see it? Sorry. So from 2.6 to point P, because if you do this, then you get, this is just equal to 0.3 seconds. Okay, that's 0.3 seconds. So what is T at the point P? If from 2.6 to the arrow is 0.3 seconds, then the time at P is just 2.6 plus 0.3. Can you see that? So your time is just 2.9 seconds. Okay, I like this method of doing it, but we can also go and use our equations as well. Okay, so we're going to use the equation now. So this is the one where you could do it. Just say 3.2 seconds minus 2.6 divided by 2. So halfway is 0.3, and then add it to 2.6. So when we are looking here, we can see that the initial velocity here is 2.94. Okay, so then let's go calculate. So we can just use this part of the graph now. From here, just this part. So we can find the time interval for that little bit there. And we should get 0.3 because it's a different method to calculate the same thing. Okay. Okay, so that is 3.3. Okay, so 3.3. You could also say VF is equal to VI plus A delta T. And the final velocity is 0. So when it reaches the maximum height, its initial was 2.94 from the graph plus, sorry, and then A is minus 9.8 delta T. Delta T. And then if you solve, you will just get delta T is equal to 0.3 seconds. 0.3 seconds. Excuse me. Therefore, T at point P is going to be 2.6 plus 0.3 seconds. And that's equal to 2.9 seconds. That's the answer to the question. Calculate the time at point P indicated on the graph. Okay, so that's the point P. So at that time, it's 2.9 seconds. Okay, so the next question is, calculate the maximum height the ball reaches after the first bounce. Okay, calculate the maximum height the ball reaches after the first bounce. Okay, so for the first bounce, now we know that the velocity is 2.94. So this is 3.4. Okay, so let's do this. So 3.4, we can just do it as VF squared is equal to VI squared plus 2A delta Y. So the final velocity is 0. The initial is 2.94 plus 2 minus 9.8 delta Y. Okay, so you do this now, and you'll get that delta Y is equal to 0.44 meters. Okay, calculate the maximum height the ball reaches after the first bounce. So that's the answer. Okay, again, we're asking us now to find the maximum height. It's a V versus T graph, so the area under the curve is going to give us that value as well. So I'm going to say, or delta Y is equal to area under the curve. Okay, it's calling it a curve even though it's a straight line. Okay, so let's go look here now. What we're talking about. The question is calculate the maximum height the ball reaches after the first bounce. So now we've messed it up. Blue. So this is the part I'm talking about now. See here, this triangle. That's the area under there. Okay, so it's a triangle and it's a half base times height. Now, what is the base? We've already calculated this time. It's just 0.3. So a half of 0.3, and what's the height? It's just 2.94. Can you see? So area under the curve, which is just a half base times height, which is equal to a half, 0.3 seconds, and the height is 2.94 meters per second. And if you do that, I'll just bring it down because we can see the answer there already, 0.44. Again, it's two different methods. You can choose whichever one you prefer. You must get the same answer. You will get the same answer. So V versus T graph, you can calculate the displacement or the height by finding the area under the curve or by using your equations of motion. Okay. Now the last one. The last one says 3.5, calculate the distance between the ball and hot air balloon when the ball is at its maximum height after the first bounce. Okay, so you have to read the question very carefully. So the ball falls and it bounces. So after the first bounce, it reaches the maximum height. Okay, so when it reaches the maximum height after the first bounce, what is the distance between the ball and the hot air balloon? So remember, all the time, the hot air balloon is just going upwards. And then the ball falls, bounces once. And when it's at that maximum height, we want to know what's the distance. So the way to do that is we need to find how far did the balloon go since the ball was dropped. And then we need to find out where the ball is at that time and then find the distance, right? So let's do that. This is 3.5. Okay, so what is the distance traveled by the balloon since the ball was dropped. Okay, now we need to know when did the ball reach the maximum height? Okay, so there's it here. So when it bounced, after the first bounce, it reached its maximum height here at point P. Can you see that? Point P is where the ball reached the maximum height after the first bounce. And we can see on the slide here, we calculated the time to be 2.9 seconds. Okay, so we want to know what is the distance traveled by the balloon since the ball was dropped. And this is now for the 2.9 seconds. So delta Y for the balloon is very easy because the balloon is moving with a constant velocity. Okay, so delta Y is equal to speed multiplied by time. Okay, so 5.88 and the time is 2.9 seconds. And you get 17.05 meters. That's the distance traveled by the balloon since the ball was dropped. Okay. What was the height of the balloon when the ball was dropped? The balloon wasn't on the floor. It was at some height. So height of balloon when ball was dropped. Okay, so that is what we calculated above. Okay, can you see here? 17.84, the height above the ground. So calculate the height above the ground from which the ball was dropped. 3.2, we calculated it to be 17.84 meters. So that's where I'm getting that from. 17.84 meters. So the balloon was at 17.84 meters when the ball was dropped. And then in the time that the ball fell and bounced, the balloon also traveled 17.05 meters. So what is the height of the balloon after all this time? So the height of balloon after the 2.9 seconds is just equal to 17.05 plus 17.84. And that is 34.89 meters. That's the height of the balloon, right? So the height of the balloon from the ground. Okay. Okay, it was from the ground. And what was the maximum height that the ball bounced to? Maximum height of ball. I'll just write you above ground so that we know. We just calculated that. It's equal to 0.44 meters, right? So what is the distance? So the height of the balloon from the ground is 34.84 meters. The height of the ball from the ground is 0.44 meters. So therefore the distance between them, so distance between balloon and ball is equal to 34.89 minus 0.44. And that will give us 34.45 meters. Okay. I did go a little bit faster through the last bit because a little bit over time. Okay. Hope that you are happy with that. Do you have any questions?
It looks like there was one in the chat about the areas of the triangles, but I answered that and I got a thumbs up on it. So I think you're good. I don't see any hands up or any unanswered questions in the chat.
Perfect. Thank you. So we can end the chat then. We can end this.
I think so.
Okay.
Cheers.
Thank you. Bye.